morning, all of you. My screen is visible. Hello.
Yes, sir. But there is a voice in your disturbance in your voice, sir.
Okay, ma'am. Now it is okay?
Yes, sir.
Okay. See that there is a firing circuit. So in the previous class we discussed the one circuit, that is a resistance triggering circuit. And also one problem we discussed. We will see one more problem. More or less other problems also same. Just to see that resistance firing circuit of SCR, the following parameter IGT minimum, that is IG minimum 0.5 milliamperes, VGT is a 0.7 volts. What is the meaning of VGT? Is a minimum voltage is required to trigger the SCR. Gate triggering voltage is a 0.7. And supply voltage, that is input, they mention 48 volts 50 H. So that is the input side. The resistance in the gate current path is 70 ohms. That means R1 plus R2 is given 70 kilo ohms. Find firing angle for the above condition. If I place R1, R means R minimum and RV, value is 70 kilo ohm, what is the firing angle? I said the theory part, by changing the RV, means here R2. So by changing the R2 value, this is a RV, whatever convention you want to use. Changing this, alpha is going to change, In that scenario, I want to know that if I keep RV and fixed resistance combinedly is a 70 kilo ohms, then what is the probable value of alpha? That is the one question. And second question, what is the resistance for which firing angle is 90 degrees? This is just reverse of first problem, A bit. What they given? If the resistance is this much, what is the firing angle? That is the A bit. Second case, firing angle is 90 degree I want, then what is the probable resistance I have to place it? That is the second bit. That is only slight modification. Now we will see the first one. According to this circuit, this one is a R triggering circuit. And what is the supply voltage? You can see that E is equal to, current will pass like this. So in that voltage equation I can write, what is that current? It is passing gate current, no? IG into these two resistance, sum of R1 plus R2 plus voltage drop across the diode, that is a VD, and whatever drop across the damping resistor, that is a VG. So this is our actual voltage equation. In that you substitute the given data. IG is mentioned 0.5 milliamps and R1 plus R2 is given 70 kilo ohms, and then VD, the diode drop, is a 0.6, and voltage across that resistor R or VG is mentioned in problem 0.7. So if you substitute that, we will get supply voltage. This is equal to 36.6. And now you know that what is the supply voltage? Vm sin omega t. This is the supply Vm sin omega t. That Vm, we calculated this ET from this equation 36.6. What is Vm? Root 2 into Vs. Vs is given 48 in a problem. Root 2 into 48 sin omega t. That omega t we need to calculate, that is nothing but a alpha. So now from this sin omega t is equal to 36.3 by root 2 into 48. Then omega t is equal to sin inverse of that. So sin inverse of 0.535. That will give as a 32.3 degrees. So that means if you keep R1 plus R2 is equal to 70 kilo ohm resistor, sum the resistance value, then your firing angle you will get it 32. Suppose next case I want to increase that alpha to 90 degrees instead of 32. Later point I don't want much voltage, I want only less voltage. Then I want to change that alpha. So by changing the alpha, what we have to do is, they mention that alpha 90 degrees. Then what is the probable of resistance? the sum R1 plus R2 is equal to R, let it be. You find R value. If you keep that one, you obviously will get it as a alpha is equal to 90 degrees. Same equation here, what will get ET? Vm sin omega t. Omega t is 90 degrees. That's all. Sin 90 is 1. So in that, you just calculate the next bit, B bit. You can see same formula used. So this point is Vm sin omega t. No, this is equal to Vm sin omega t. So Vm is what? Root 2 into Vs. So you just substitute root 2 into Vs is 48 is given into sin omega t into sin 90 degrees. Sin 90 is a 1. So just you will get it the equation. Now you can see that root 2 into 48, Ig is given, R is unknown now. Previous case alpha omega t is unknown, these two is given. In that case, we can get it as a R1 plus R2 is unknown, Vd is given, Vg is given. We will get it as a what is the R. That's it. So that is the second bit. If we keep R is equal to 133 kilo ohms, then our alpha is going to be increases. That is only the analysis. You can see that if I keep alpha is equal to earlier R1 plus R2 is equal to 70 kilo ohm, your alpha will be 30 something. So now what will happen? I want to increase the alpha. Then probable option is what? Only RV has to increase. If I increase the RV to reach Ig minimum, it will take more time. And if I reduce the RV, suppose if RV value is reduced instead of 70 kilo ohm, if I keep as a 30 kilo ohm, then what will happen? Automatically your alpha will be lesser than the 30 degrees. If you keep 70, you got it 30 plus something, no? So if you reduce that RV value less than the 70, obviously you will get less alpha. So that is the procedure. Just this is one of the problem. Now we will go for as a next RC half wave triggering. So what is the different? RC means resistor and capacitor. We noticed some drawback in case of resistance triggering. Major drawback is it is going to control only 0 to 90 degrees. That is the problem in a R triggering. In a RC triggering, what you have to do is use the capacitor also. You can able to control that alpha 0 to 180 degrees. That is the one problem we can overcome by make use of a RC triggering. And here RC triggering, two things are there. One is half wave RC triggering and full wave RC triggering. And one more drawback in R triggering, we noticed that what you can say that during only positive half cycle we are getting as a output voltage. During negative half cycle we are not getting. So that problem we can overcome by using RC full wave triggering. Whereas half wave triggering, that problem remains there, and later we can use RC full wave, we can overcome that problem also. So now we'll see that RC half wave triggering. This is the circuit. Here two diodes we used, one is D2, another one is D1, and as usual RV is required to control your alpha. Same thing, here also that problem is still there. By using that resistance you are able to control. That's why all these methods we cannot be used by using this RV, we are controlling the alpha value. But these are the reasons generally we don't use nowadays triggering methods, R triggering or RC triggering or something, integrated circuits we don't use. Only we'll use in the direct programming process to generate the for even DSP programming or microcontroller or FPGA controller. So all these techniques, algorithms we can use it to develop as a pulse width modulation. So the reason is all these components will power dissipation. Whereas in the case of programming part directly, you can write a code and it will generate without any loss. So that is the latest technique we use to generate the firing pulses. But now these are the conventional methods. RC half wave triggering, we can see that during negative half cycle there is a capacitor is going to be charged. What is the path for charging the capacitor during negative half cycle? Anybody? My intention is to charge the capacitor during negative half cycle. This will be plus, and this plate is plus, this plate is minus. Like this I want to charge. What is the path for charging? Anybody? During negative half cycle means this is minus, this one is plus. Then path you can see that neutral, it goes to the C plus, then C minus, then diode will be forward bias. That's why RV will be short, it won't pass through that, and diode is conducting, then this is the path. So once current is passing through the capacitor, it will charge through diode D2. Then the lower plate will be positive, upper plate is negative. So that is the reason D1 also will be reverse bias. If D1 is reverse bias, no current pass through the gate. Our intention is whenever I want to turn on the SCR, at that instant only it has to on. For that reason, during negative half cycle, we need to charge the capacitor. Upper plate is negative, lower plate is positive. Once if it happens, it reaches to as a same as the source voltage. After that, during positive half cycle, what will happen? So now it is known that this is minus, this is a plus. It is already charged during negative half cycle. Once if there is no discharging path, it will hold same magnitude. Now let it be T charged minus V maximum during negative half cycle. So now this magnitude remains there in the capacitor. After that, during positive half cycle, this will be plus, this will be minus. Then what is the path for discharging? Here means that discharging is nothing but a charging in the reverse direction. Because of the capacitor, you can see that already negative polarities are there, or there is a minus in this side, lower is plus, that is a minus V max. Now what I want is, if I keep this voltage across this is equal to the VGT, what is the meaning of VGT? I already mentioned this much voltage is required across gate and cathode to trigger the SCR. That is a fixed point. VGT is a gate triggering voltage. Voltage across gate and cathode is equal to the VGT, then automatically SCR is going to trigger. In that point, how much voltage I have to get it gate and cathode? You can see that here is a gate, this point is a gate, and this point is a cathode. So in between these two, I need to make the voltage is VGT, some value. The VGT value will given in the specification. Let it be some voltage I need. So now what I have to do is, during positive half cycle, plus and minus, it is going to charge through resistor and capacitor. This is the path for charging the capacitor. While it is charging the capacitor, already there is a minus sign is there. Now while you are adding positives, suppose minus 100 is there, you are adding positives 10, 20, 30 and so on. What will happen? The resultant will reduce, no? Minus 100 plus 10, 90, minus 90, then plus 10, then minus 80 and so on. You are adding, or you are charging in this direction, or you are adding the positives, then what will happen? Automatically, one certain point of time, this will become as upper plate will be positive, lower plate is a negative. Means all negative will vanish and reaches to the zero and start charging in the positive side. So that's what you can see the dotted line. It is a minus V maximum during negative half cycle. After that, during positive half cycle, you can see it is gradually charging the towards the zero side, and the negative minus V maximum, and then towards the zero side it is charging. Once the 0 point reaches, again it will charge in the positive. How much it has to charge? It has to charge up to the VGT only. Once if it charge VGT, automatically this diode will forward bias, because upper will become as a 0 and then positive, no? Positive is connected to the anode of the diode, and then automatically diode will forward bias. Once diode is forward bias, what will happen? This will positive, no? Once it reaches to positive at this point of time and it reaches VGT. If it reaches VGT, then diode will forward bias. If diode is forward bias, then the upper plate, capacitor upper plate is directly connected to the gate and lower plate is directly connected to the cathode. So therefore, voltage across gate and cathode is equal to the VGT. over. Our problem is solved. So once that voltage reaches to the VGT, automatically thyristor is going to be trigger, because voltage across gate and cathode is equal to the VGT. Automatically thyristor gate terminal reaches to Ig minimum, then thyristor is going to start conducting. Then if thyristor is conducting across the load, whatever the source voltage is, because this is on, no, the diode thyristor is on, this end is connected to negative, this end is connected to positive, then the load voltage same as the source voltage. What is the source voltage after conduction? It will become as a same as the source voltage. Load voltage is equal to the same as the source voltage once the point reaches to the VGT, and it will hold same small magnitude in the capacitor that remains there. And again, during negative up cycle, what will happen? Again, capacitor is going to, because upper is plus and lower is minus, no, now again it is charging in this path, D2 and then source. Then what will happen? Again it will become as a negative. It will hold negative. Then positive side. Positive side it will charge through RV. Then the question is, how to vary the conduction angle or alpha, for delay angle. This alpha, now we are getting this much time to trigger the SCR. So that is the alpha. Now I want to increase that alpha value or decrease that alpha value. What I have to do? What is the option? You can see that from minus V maximum to VGT, to reach that charging or in the reverse charging, tau is a time constant, that is equal to RV into C, no? C is fixed. So RV. So if I keep less value of RV, then what will happen? To reach VGT, it will take less time. Now we'll get it like this. Here it will start conducting. Now your alpha will be, this is your output, and your alpha will be only this much. Why this much less? Because I keep RV is very less, therefore very faster rate it will change over from minus V maximum to the 0, and then it become as a VGT. VGT is very small voltage only, because gate and cathode only we required to get Ig minimum. It is after all is a milliamperes of current we need to pass. So therefore, to get that VGT, how much time it will take, that decided by the RV. That is only the alpha. Now, if I keep RV value further more, then if I increase the RV is more, then what will happen? It will take more time to reach VGT. Then from minus V maximum, and then gradually is rising, and somewhere it will touch that VGT. Then this is your alpha. Now our output will be like this. This is your output. Then this total gap, I call it as a alpha, like this. So from this, what is one observation is, by controlling the RV, we can able to get the alpha variations. So that alpha variation is beyond what we call it as 90 degrees also. At anywhere, only charging capacitor is used to fire the device, and in addition to that resistor. So that is the reason we call it as RC triggering. Half wave means that we are getting only during positive up cycle, because this we required positive, and I want the negative up cycle also pulse. Then what I have to do is, I have to make it all half cycles into the positive half cycle alone. If I keep AC supply, you can see that there is a positive and then negative, but to get conduction, I want only positive. So what I have to do? I have to convert this AC supply into only positive cycles. So that means negative half cycle also need to become as a positive half cycle. Then only I can get here is another firing pulse. But how to make it that? That is only the RC full wave triggering. So now this is RC half wave. You can see that whatever I explained so far, variation of the R. If I keep R value is very high, let it be IR, then what will happen? Minus V maximum, and to reach VGT is taking much time, and it will hold very small magnitude. It will remain there once the device is conducting, and then only this is the your output voltage and this is your alpha. If I keep all RV is very high, large RV otherwise. And now if I keep RV is low, then time constant is low. So time constant is low in the sense from minus V maximum to touch the dotted line, that is VGT line, it will take only less time because time constant is low, so it will charge very faster rate. So in that way we can able to get it as a variation of the alpha. So there is a empirical relation. You can see that there is RV into C must be greater than this one, and as usual of expression of E, that is equal to I into RP plus VG plus VD1, because there is a gate voltage will be there, and diode also we use, the drop also you can consider. This is some just ES formula. And now use this graphs also for observation of RV is less and RV is high. R means that R in our notation. So high value of RV and low value of RV, we can able to control that alpha. So then we'll move on to full wave triggering. So in a full wave triggering, what you can say that you have to convert that into only all positives. What is the controller I have to use to make it all positive? Anybody? What? AC supply, make it as to all positives means DC. Use a diode rectifier, that's it. Say same AC supply, remaining portion is same, nothing is different. And now we don't require to use all diodes and all, because here itself we are getting as a all positive cycles. So now use the diode rectifier, you can get it as a what you call it as all positive cycle, just D1, D2. So during positive half cycle, current will pass like this. Let it be, I want to measure voltage across this VD, and it goes to the VD and D2 to out. And during negative half cycle, this is minus, this is plus. It goes, there is a positive D3, and will again come back T4 to out. So with that we can able to get it. Input is AC supply as usual, and positive and negative half cycle we are getting as a this one for positive half cycle, for negative half cycle again positive half cycle, and so on. So for positive half cycle D1 and D2 is conducting, for negative half cycle D3, D4 is conducting, and again D1, D2. So with this this is a supply Vs, and this one is a Vd diode across diode rectifier. Now you know all the things are positive. Now it is easy to control alpha value during positive half cycle as well as the during negative half cycle. So now we'll see that this is input. I am using as a diode rectifier to convert AC to DC. This will become as a VD, and now you draw one line, that is a VGT. This is a reference. We need to know when it is going to trigger. Once that charging the capacitor is reaches to the VGT, automatically the gate current is IG minimum and SCR is going to be trigger. So now what will happen during, anyhow all the things are positive. Now it is charging through RV only, and once it reaches to the VGT, then SCR will trigger, and here is a firing pulse will be generated, and again it will hold very small magnitude, or let it be 0, and again positive half cycle it will charge and it will trigger, and so on. So this is the way we are able to control your positive half cycle as well as the negative half cycle. So but only the thing is, only one pulse is generating, whether positive or negative. If I want to fire many number of devices, so many such type of circuits are required. In this case, RC full wave triggering. So to overcome that drawback, what we have to use is you can go for as a UJT ramp triggering. So that we'll see after this. So like this, voltage across the thyristor. This is, as you know that if it is in the off condition, same as the source. What is the source? This one. And once it is on, it will be 0. Again off condition, same as source. When it is on, it will be 0, and source, then once it is on, it will be 0. Again by controlling the R here, you can able to control the alpha, whether it has to fire here, because if you use low R, automatically it will trigger only at this point. So then your firing angle will be like this. This is only your alpha. This is alpha and this is your output. And voltage across the device, what is the modification? Only up to this it will be on, then rest will be 0. This one will be 0, like this. Again it will be on like this, then it will be 0. And again it will be on like this, it will be 0. So like this we can modify whatever may be the alpha, we can easily control by controlling the RV value. That is what RV is equal to high. It take much time, then alpha will be more. If RV is less, it will take less time. Just now I drawn, no? So less time will conduct here itself. Only the small value is the alpha, because we use the R is small, then time constant is very small. It will charge very faster rate, then automatically it will get it VGT soon, then it will trigger. So that is what this is the empirical relation RC greater than 157 by omega. So that is the value of RC we have to consider. And now we can see that UJT. So this is a uni-junction transistor. First, before using this UJT in our circuit, in a ramp triggering or UJT triggering, we'll see what is the small mathematical relations of uni-junction transistor. You can see that it is only one junction, like a PN junction here. So that is equivalent circuit of UJT. Terminals are B1, B2 and E emitter. And now this is the representation. There is a junction present here, that's why I used as a diode here, and RB1 and RB2 will be there. And now we can see that intrinsic standoff ratio, this is the RB1 by total resistance. So the equivalent device symbol you can represent like this: emitter, base 1 and base 2. So now this is our device, when the device is going to trigger and when the device is going to turn off. So that things we'll discuss first, and then this device will make use in our circuit. So that is only different. Now once if you use this device, we should know that when the device is going to fire, at what instant. So now this is the point we have to vary the voltage normally. If this voltage is beyond some certain value, automatically device is going to trigger. What is that? We will see now. So that is the uni junction transistor is nothing but a only one junction will be there. I have to use that junction to break. Once if you break the junction, automatically what will happen? Device will trigger. If the device is trigger, I am audible, no? Anybody? Hello?
Yes,
Yes,
sir.
Okay. Now the typical range of eta, that value is 0.4 to 0.8. This is the ratio value will be this one. And now we can see the equivalent circuit, same thing. What is our intention is, I want to vary this emitter voltage, because there is a terminal emitter, base 1, base 2. So I vary the emitter voltage, and this voltage VB1 is reaches to some certain value. That value is a peak value or required voltage. Like a thyristor, I said no, VGT. What is VGT? Gate triggering voltage. So that is the minimum voltage is required to trigger the SR. Similarly, in the case of UJT, to break that junction, we required some voltage. So that voltage we call it as a peak voltage. Now we can see the relation. I want to know what is this voltage. Just potential divider rule. So VB1, that is equal to total VBB into RB1 by RB1 plus RB2. So this ratio, as I said earlier, eta, that is a VBB into eta. So if this is reached, VB1 is equal to eta into VBB, so that is the voltage across that junction. So now if emitter voltage, you can see that less than that and greater than that, based on that whether the device is going to be turn on or a turn off. Device means here junction is going to break down. So to break that junction, we required some voltage. What is that voltage? Suppose emitter voltage is greater than this, VD is because of some small drop, 0.7 something, plus N eta into VBB, this voltage. So VD plus N VBB is, this value is less than the VE. That means VE is greater than that voltage. So we need to increase that voltage must be greater than this. Automatically that is a sufficient voltage. So normally it is up to N VBB only, but there is some drop is there in the junction. We need to consider the drop also. It is only 0.7 volts. So if see that applied voltage or emitter voltage more than this, then automatically the junction will be breakdown. It starts conducting. There is this all together is a device. So our intention to break that junction or conducting the device. In that case, I can say the device is going to be on. Otherwise, if emitter voltage is less, then what will happen? Automatically, device is going to be turn off. VE is less than VD plus eta into VBB, then the device is unable to trigger. So this is the logic we require when you are using in a circuit, because it is only the device I am telling, if when the device is going to be trigger and when it is going to be off. So that means if that voltage, emitter voltage is more than that, it will be on, otherwise it will be off state only. And that's what I mentioned here. You can see UJT and current will flow through RB1 because this is the path for RB1. Hence the temperature will increases. These resistor will be decreases. This is a negative coefficient. You can see that when the current is passing through the resistance, what will happen? Temperature will increase. Once temperature increases, resistance will decrease. If resistance is decreases, further temperature is going to be increases. So that is the negative coefficient. Now we can see that the point you can notice that VE is a emitter voltage is increased, then emitter current also will increase because it has to pass through the RB1, and the junction behaves like a PN junction because this is the junction has to break down, that will behave as a PN junction. But VE can be only increased up to the particular value. That value we call it as a peak value. So now we are increasing up to the peak. Once this is the required voltage. What is that required voltage? VD plus eta into VBB. So if that voltage is increasing gradually, then the peak voltage reaches, then immediately what will happen? The device will start conducting. That means junction is going to be breaks down. Then UJT is going to turn on. Once UJT is on, this resistor VB1 resistance is very less, 47 ohms or something like that, very less ohms. Then sharply current will decreases and sharply current will passes through the RB1. So that sharp spike will be as a pulse. That pulse you can connect it to the our thyristor. That is only, we need to generate a firing pulse here, very spark pulse, because of very less resistance here. Once the device is triggering, it will be. So now that's what you can see that once VP reaches, device will turn on. This increase the conductivity, then the temperature increases, reduce the RB1. That's what I told. Now RB1 gradually reduces. It is very small value, and this results in the condition where the emitter current is increases and emitter voltage will be decreases. Now you can see that gradually it is decreasing the voltage. Once this voltage reaches to the value voltage, then this device cannot be withstand in the on state. That is the reason we can say that again it is going to be as a off position. From this 2 points need to remember, if you increase the emitter voltage up to the VP peak voltage, what is the peak? VD plus eta into VBB. If you increase the emitter voltage up to VP, device will trigger, and if that voltage is dropped down, means discharging will be reduces to the lower value, that is a value voltage, then the device is going to be open. Our intention, UJT requirement is like a switch. In our case, what we want to use switching operation, when it has to be on and when it has to be off. While it is turn on the device, that spike pulse we make use to trigger the SCR. This is the basic of UJT I am explaining. Now will start using. That's what I mentioned. Value voltage is negative slope. Once it reaches to value voltage, automatically device is going to be off, turn off. That will not be withstand to conduct continuously. Then the device is going to be turn off. Then fully saturated, then the device beyond that value point, the UJT is going to be off. That's only the sentence here. Now we make use of UJT and use this is actual our triggering circuit. Whatever I shown you in the previous slides, that slides about the UJT, how that nature of that UJT characteristics and all. Now we make use that UJT to trigger the SCR. That is the reason I call it as a UJT triggering. So what is the UJT triggering? We can see that supply is given. Now I close the switch. If I close the switch, what will happen? You must understand the circuit operation, because this is not only one circuit or two circuits. It is in each unit you may have plenty of the circuits and waveform. Only thing is, any circuit, try to understand the operation. Once if you know that operation, you can easily draw the waveforms, all these things. Now let SW1 is closed. Then what will happen? Anybody? Our intention is very clear. I want to turn on the UJT. How to turn on the UJT? Voltage across the emitter and base one is equal to the value of peak voltage. Then it will trigger. That's it. Then what is the operation now? Anybody? Anybody tell me what will happen if I close the switch SW1? Means it is nothing but supply we connected. If you want, you can use like this also, no issue. This is the some voltage is given, let it be whatever voltage I mentioned. Then the supply is given, this switch will close. Then what will happen? Path. See that? Current will pass like this. That's all. So what is happening? Whatever R value you place, based on that, capacitor is going to be charged. What is the charging time constant of a capacitor? R into C. So this is the charging time constant. Then based on R or RV, whatever, if you want, you can keep like this also, variable resistor, it will charge. Now once it is charging, what will happen? This will gradually rising now. See, the capacitor is charging, gradually rising. Once it reaches to the peak, then what will happen? UJT will trigger. Means this will break the junction and UJT will on. If UJT is on, is there any path to discharge? Capacitor is already charged plus and minus. And once it reaches to the VP, then what will happen? This is going to be discharge that capacitor. What is the path for discharging? Through RB1. So this RB1 is very low resistance, sharply it will decrease. And that decreasing this portion, the sharp decreasing portion, you will get it as a one pulse. That is the pulse. This pulse is connected through gate. Because there is a one resistor, I used here large resistance value to limit that current, because very high spike pulse will be obtained there. To minimize that, we are using as a one protection resistance to gate circuit. So now that only I will represent in the waveform fashion. Now you can see first step is supply is given to the circuit and capacitor is going to be charged. Charging time constant is a R into C. This is the, see that circuit, capacitor is going to charge. Capacitor charging time constant, let it be tau 1, RC, that is a capacitor charging time constant. When it will on, now the UJT is open only. Once the charging the capacitor is equal to VP, that is a peak voltage. Once that voltage is reached, automatically UJT will trigger. Once UJT is triggered, then it is passing through resistor. Then the resistor value is small, very sharply. While it is charging, it is taking time because of this resistor value. Even if I reduce this resistor, charging also will get it very faster rate. Then you will get alpha value is small. That's all. So now it is charging this much time. and then it is gradually, means very sharp rate, gap is very small, because discharging time constant is very small. This is only ohms, this may be kilo ohms. So then what will happen? This will be very sharply decreasing. So once the switch is closed here, that sharpness is become as a pulse. That pulse is connected to the gate. Then automatically SCR is going to be triggered. So that pulse only we represented here. This is the pulse. Like that, charging and discharging every instant, you will get it as a pulse. Device is going to be triggered. So now the question is how to vary the alpha. Again, same logic. So here this gap, we call it as alpha, no? Because here x-axis mentioned t, that's why they used as a alpha by omega. Normally if you use omega t, this is nothing but a alpha only. So now I want to decrease the alpha or I want to increase the alpha. What I have to do? Again same R value. If time constant is reduced, means less, then charging will be again faster rate it will rate, and discharging will be like this, then your pulse will be here. That's all. So this is your pulse. Only this much is your alpha. Like this, again we are charging this. Now we'll make it as a charging, and discharging is very sharp rate. This is getting as a firing pulse. Now this is alpha, like this. So what we want to do is, you are changing the RV, we can able to get it as a firing pulse. Now without using gate current or what you call it as gate voltage VGT, now we are passing as a firing pulse. That pulse is given to the gate, then automatically SCR is going to be triggered. And another one, we can see that ramp triggering. Here this setup is required, one setup to trigger the SCR, and similar setups are required to trigger another SCR. But series operation of SCR, all the SCRs are maybe in HVDC transmission, the string, that whatever SCRs are connected in series and parallel, all SCRs must trigger at the same time. So for that we can go for as a another mechanism. Same we are using as a UJT only, but synchronized UJT triggering or ramp triggering. So this is the another method we use to trigger the SCR. That we can see this circuit modification. We can notice this portion is as usual. You can remember previous circuit and this circuit. What is this? Again UJT only we used, and then the resistor I used, variable resistor, capacitor. Only thing is this portion. So this portion is one additional, because that is also same. Earlier I used directly DC supply, that's why I didn't show the diode rectifier and all. But now we used as AC supply, that's why we used as a diode rectifier and converted into AC to DC, and we are passing through the UJT terminal. But only modification in this with previous circuit, we can see this portion. What is this earlier? It is a RB1. This is earlier one. It is a RB1. Sharp pulse will be there. Instead of that, what I used is a transformer, magnetic coupling transformer. We use tightly coupled between primary and secondary. Now you can see that there is a secondary is going to be splitted, many number of secondaries. If I split secondary 4, then whatever pulse is present in the primary, automatically same pulse will be induced in the secondary. That will be 4 pulses will generate. Each pulse you can connect it to one SCR. So that way we can easily generate 4 firing pulses or 5 firing pulses, like that. All SCRs we can able to trigger at the same time with using only one circuit. So that is the advantage. Now we'll see the operation as usual. It is all circuit operation. Now anybody can analyze this circuit. Is it required any explanation? If you understand the previous things, it is very easy to analyze the circuit. That's why all the circuits are interlinked. What you want to do is, you try to make use of analysis. So that way we can easily understand writing the theory also in exam point of view. Only 2-3 steps are sufficient. if you don't feel that I want to write 2 pages, 3 pages, you don't get any marks with that unwanted explanation. What is required is circuit and operation. How that is going to be operate for related to your waveforms. That's it. Now, by seeing this, even without waveforms also, we can able to analyze. Supply is AC. We can draw how to write, what you call it, represent the waveforms. First, supply AC. You draw one AC supply. Then diode rectifier. What is output of diode rectifier? Keep it as a VDC. Input is VS. Draw the supply. Then second waveform is a VDC. What is the waveform? Make it as a all positive of cycles you can represent. Then there is a resistor to smoothen that current, and as well as the linear diode, it will clip that voltage some VZ value, because even if you are changing the input side fluctuations, we don't want to fluctuate that, because UJT is required some fixed voltage to the UJT device. For that we clipped that, and then once if you know that voltage, as usual again that voltage is charged to the capacitor. The charging constant is tau RC, and then once if it reaches to the VP, then UJT will trigger. Once UJT is triggered, that pulse is connected to the primary of a transformer. So whatever pulse we are obtaining, that pulse is given to primary of transformer, and then automatically secondary pulse will be reduced. So once if we give secondary pulse, then what I have to do? There is a thyristor. This is the firing pulse, and another thyristor I can use like this. Any number of thyristor based on your. So this is a gate, and cathode you can give like this. Then second gate, second cathode. If you use another secondary, you can able to use one more thyristor, gate and cathode like this. But you cannot be split secondary many number. It will reduce the mechanical strength of the transformer. So that is the reason we must use some certain based on the transformer strength. We can split the secondaries. So only thing is we have to generate the firing pulses in the primary side. Same pulse will be that many pulse at the same time will be induced in the secondary side. Each secondary is connected one of the thyristor. So all the thyristor at a time it is going to be fired. This is we call it as a ramp triggering. Now you can see waveforms as I explained just now. Same thing. First we have to represent AC supply, that is a VS. Then diode rectifier like this. Once if you analyze circuit now, exactly we can able to draw the waveforms. So now VD, this is a diode voltage, diode rectifier voltage, all are positive. D1, D2 will forward bias during positive off cycle, and D3, D4 is forward bias during negative off cycle. And now we use it as a linear diode, that's why we make it as a constant voltage. We are clipping that, and now after that charging and discharging. What is this is a N into VZ, that is our required voltage to trigger the UJT. So the transformer ratio, all I mentioned 1:1:1. That means whatever voltage induced in the same pulse will be generated in the secondaries also. So now what will happen? You can see that it is gradually charging. What is charging? R into C, tau, charging time constant. Once if it reaches to the peak voltage, that is a eta into VZ, and then UJT will trigger. UJT is triggered, then it is low impedance offered by this primary winding, then it will be sharply decreases. So that pulse is generated in the primary. So once if you generate the primary, automatically secondaries also will induce that, we can connect it to that. Then once the thyristor is connected, if you connect something load at that point, if you connect load here, whatever, then whatever the device is conducting, this will be same as the source. That's why we represented as the source here like this. So this is the operation. It is also important question they asked that explain the ramp rate limit. If without asking any specific, if they asked you to explain triggering method or any one of the triggering method, you can use any one. Otherwise they may specify, use that. If it is essay question, they ask to explain the triggering methods of SCR, you must explain all the three. So this is the one of important essay question if they ask separately. Now, we can go for next one is a commutation methods of a thyristor. What is the commutation methods? What is the commutation? Anybody? Anybody? Let me know what is the commutation. In the initial classes itself, I told no commutation is the process of turn off the device. So that is nothing but a commutation. So process of turn off the device is a two process. So one process is we can see that natural commutation or a line commutation. Another one we call it as a forced commutation. So natural commutation means that without using any additional circuit, thyristor is going to be turned off naturally. That means current passed through the device is below the holding current. That we call it as a natural commutation. What is the holding current? It is a minimum anode current below which device is going to be turned off, and that is we call it as a commutation. So if without using any additional circuit, naturally supply voltage goes to natural zero every positive off cycle, negative off cycle, it means every pi 2 pi 3 pi and so on. During that instant, automatically device is going to be open. That is a natural commutation. Another one is a forced commutation. So what is the forced commutation? By if input is DC supply will never go to natural zero. You have to use some additional circuit, that is a commutating circuit. Make use of that commutating circuit. You are going to turn off the device. That commutating elements L and C, we make use of commutating elements L and C to turn off the device. That we call it as the commutation, or I mean forced commutation. Forcibly you have to bring that current pass through the device to the zero or below the holding current. That is a forced commutation. In this, forced commutation techniques are there, are class A, class B, class C and so on up to class E, and class F I call it as a natural commutation. So now we can see that small introduction. Thyristor can be turned off when the anode current is reduced to below the holding current, and reverse voltage is applied across the thyristor specified time, so the device reverse to the blacked state. That is also called as up state. There is another way. Reverse voltage applied across the device, automatically thyristor is going to be turn off. Or very simple, no, current is passing one direction. If you same force if you apply in the reverse direction, then the resultant current will be zero. Then the device is going to be turn off. So that means reverse voltage applied across the device, then also device is going to be turn off. And then forward voltage can be reapplied after certain time. Why that certain time? So that X is a charge, that's what I explained in the dynamic characteristics case. X is carriers in the outer and inner layers must decay to the zero level. So even like a fan, no, I switch off the fan, it will rotate some more time. So that is charge particles are present, or you can see that kinetic energy is stored in that inductor coil. To dissipate that, it will take some time, completely dissipated, then it will be zero speed. Similarly, in this also, once if you reuse that operation, you have to wait some time. That is a all charge particles must be removed. The process of turn off the thyristor is called a commutation. There are two types. One is natural commutation or a line commutation. So the natural commutation is without using circuit, and forced commutation point of time. At 0 also you can put it, or 30, 60, 90, anything, somewhere you have to put a firing pulse, because only one thyristor you can give only one firing pulse for positive off cycle. Now pulse is given. Then what is output voltage? From here to here is 0 output. From this point onwards, device will start conducting. Your output same as the input. This is your output. Then at pi reaches due to natural commutation, thyristor will be open. That is only a sentence is required. And then open means it will be 0. Again, pulse is available, it will be on, then it will be 0. That's all. Natural commutation is over. This is your output voltage waveform. You want current waveform also reduced to some magnitude. Voltage and current are in phase because resistive load. Explanation part: during positive off cycle, thyristor is forward biased. At an angle of alpha, pulse is given to the thyristor. Thyristor starts conducting. How long? From alpha to pi. Once pi reaches, supply voltage is 0, load voltage also 0, and because of the resistive load, current also 0. And once current pass through the device is 0, thyristor is going to be open due to natural commutation. Over. That is only the explanation is required for natural commutation. Next one, voltage across the device. I already mentioned the logic. Off state, same as the source voltage. On state, 0. Here alpha to pi is on, no? I made it 0. Rest of the thing, same source voltage. Wherever device is on, you make it 0. Rest, you just copy the supply. Whatever supply is there, during off state, you can draw as such supply, and on state, make it 0. That is the voltage across the device. So this is the natural commutation. In next class, we'll see the forced commutation. Okay, if you have any doubt, you can ask me. Otherwise, you can leave.